Hi everyone, today I'm gonna talk about our papers, Transitivity-Preserving Graph Representation Learning for Bridging Local Connectivity and Role-Based Similarities. My name is Thuy Hoang. I'm from the Catholic University of Korea. Graphs are everywhere. We can see graphs in transportation system, social media, chemical networks and programs, and graphs are a general language for modeling the complex systems. Over the years, GNNs as state-of-the-art representation learning methods and GNNs interactively aggregate the information from the labels and then update the information to generate the representations. And nodes we have embeddings at each layers. However, there are several limitations of existing studies. First, most existing methods only encode the positional and relations between the pairs of nodes rather than discovering the structural similarity surrounding structures. For example, Laplacian positional encodings cannot fully capture the similarities between the surrounding structures of adjacent nodes. For example, the node 1 and the node 3 have different initial positional encodings even though they are quite structurally similar. As a result, the models could not learn structural similarities between pairs of nodes. Second, most existing methods lack the power to capture the long-range dependencies between the nodes. It means that nodes with similar structural identity should be close in the latent space without considering their position in the graph. And moreover, most studies lack the power to integrate the load feature information and structural information, for example, the rows of nodes, into unified representations that could benefit the various downstream tasks. And here are several research questions. The first question is how to identify the surrounding structures of nodes. It means that nodes with similar structures should be mapped close in the latent space, and nodes with different structures should be far apart. And the second question is how to integrate the load feature information and structural information into unified representations. And the last question is how to preserve the global graph structure. And here is the overall architecture of our proposed model, Unified Graph Transformer Network UGTs. UGT is composed of three blocks, sampling context nodes, building modules ID and M, and pre-training blocks. The modules are pre-computed only at the first time, and then the learned representation then could be used for various downstream tasks. First, we propose assembling context nodes by structural identities. Our model can capture the similarities between nodes through their structural identities, and given a target node, we define the context nodes that are within K-hope neighborhoods, and also we sample the distant nodes with structural similarities. Uh, we we construct the virtual edges connecting to distant nodes. So here our objective is if two nodes have similar degree, they will be close in the latent space. And if their labels also have similar degrees, they are more close and so on. So in here, we construct the ordered degree sequence of labels for each node up to K-hope and then we calculate their distance based on the degree sequence. Next, we propose a new cell attention and structural identities. First, we construct the structural distance between two nodes based on the row of nodes, and then we identifying the transition probabilities between any pairs of nodes uh, M, and then we construct the structural identity for each substructure um, by combining each structural identity for each node uh, to the output of the cell attention score. So our objective is to let the model distinguish non-isomorphic substructures. Thus, we propose a self-supervised learning task to preserve the global graph structures. We change UGT on pre-take tasks to learn the graph structures without using any neighbor information by using true node functions. We maximize the transition probabilities of paths collecting any two nodes against the probabilities of other pairs not come from the graph by using noise contractive estimations. In here, we use two nodes is including noise contractive estimation to preserve the transition probabilities and the node raw feature reconstruction. For the experiments, we compared our models to state-of-the-art GNNs and graph transformer models on 21 benchmark datasets, including air traffic networks, web page networks, citation networks, TU datasets, OGB datasets, and strongly regular graphs datasets over four downstream tasks: node clustering, node classification, graph level tasks, and wave failure elements isomorphism testing. On the node clustering, in terms of the conduction and the modularity measurements, our model outperforms all the baselines that ignore the graph structures. And interestingly, the performance of our model combined with K-mean also show significant performance over the benchmark datasets. On the node classification task, utilities with pre-training outperform the baseline models that overlook the long-range, long-term dependence in most datasets, and it also shows significant improvements in homophonic graphs, for example, the Cora and Size here. On the graph level classification task in terms of ACC and AUC score, our model show competitive results compared to ZNNs and in capturing the global structure information in the whole graphs, and especially for the molecular datasets, uh, more HIV dataset, our model slightly outperformed the mainline, showing the ability of our proposed model to learn the large-scale graphs. On the power of our models, and in here we can see that our model achieves the third dimensional wave failure element test in terms of distinguishing non-isomorphic graphs. In conclusions, we have proposed a novel graph transformer utility to learn the local and global structural features and then integrate them into unified representations. And our proposed model captures the long-range dependencies between nodes with similar roles using structural similarity-based templates. In the future work, we plan to extract the structural information in communities as nodes within communities tend to share underlying similar features. And moreover, we focus on the low degree nodes as most existing models perform poorly on the low degree nodes. Thank you for listening.